Hey everyone, my name is Thomas,
I'm Rylan.
I'm Omar.
and in this video we'll be giving a progress update and performing a demo of our custom multi-threaded RISC-V network processor.
So we had a 3-week timeline for our RISC-V processor design. In the first week, we implemented a RISC-V ISA onto our 5-stage pipeline processor. From there, we also created a RISC-V assembler, and then to verify that everything worked, we ran bubble sort on hardware. In week 2, we connected our processor to the network part of the NetFPGA, and then we added a network FIFO so our processor could uh, work with the packets traveling through the NetFPGA. And then to evaluate performance, we used iPerf and TCP-dump. Finally, in week 3, we added multi-threading features to our processor.
In this presentation we'll be giving a brief overview of Deter, NetFPGA, and RISC-V. We'll then talk about interacting with our CPU and the custom network FIFO we created. We'll then go over the hardware and software changes we made to implement multi-threading, and finally we'll wrap things up with a demo and some concluding remarks. So the key part of this project is the NetFPGA. It's a network-based FPGA that has 4 1 gigabit Ethernet ports. And with this, we can deploy custom hardware modules in a network environment and interact with them using custom software running on the control server. For this project, we were very lucky to have access to a platform called Deter, which allows us to deploy custom network topologies in a real-world data center. And in those topologies, we can customize various link and node parameters like delay, packet loss, and bandwidth constraints. We also have access to FPGA resources, so we can deploy custom hardware on our custom topology.
So this is a simple 5-stage processor that we implemented the RISC-V 32i ISA on. Notice that there isn't a hazard detection unit or a forwarding unit. This is because we plan to use a 4-way multi-threading later on. So by the time that one thread is in the write-back stage, that thread won't occur again until the data has been written back to the register file. So we won't have any data hazards. Also, we modified the ISA slightly to work with all 64-bit data instead of 32-bit data.
So one of the things we need to do in this project is interact with our custom hardware. And we do this when we're loading instructions into our instruction memory and setting the initial condition of our data memory. Also, after our program finished executing, we need to read our data memory and see what happened. And so we do this by setting up software registers that we can write to and hardware registers that we can read from. We also need control bits to determine if we're accessing data or instruction memory, and also determine if we're doing a read or write. Now, let's say we're doing a write to our instruction memory. Well, the first thing we do is disable our CPU and turn on the ability to write to our instruction memory using that write enable port we can see in the diagram. We then set our address to 0 and write data to the associated data register. Now that address is then incremented and the remainder of the program is written into the instruction memory. And that's essentially how we also do our data memory interaction. So when we set our data memory, and also when we read from our data memory in our CPU. Now it's also important to note that when we're interacting with our data memory, we have to disable the output of our instruction memory. So instructions do not pass through the pipeline and interact with our data memory.
To allow our processor to access packets, we created a packet FIFO that could be implemented within our processor. This pretty much works with the controller that looks for the beginning of a packet, right? And then it loads the packet into the FIFO. Once the packet has been loaded into the FIFO, it lets the processor know that it can begin operating on the packet. When the processor finishes its operations, it will then tell the controller that it can release the packet, and then the packet will exit the NetFPGA. So we added our packet FIFO in the MEM stage. This allowed us to treat the packet as extended memory. So currently our data memory ends at address 511, but when we added the packet FIFO, the first address of the packet FIFO will be address 512. Once the packet is loaded into the packet FIFO, the processor actually has the ability to access any 64-bit word within the FIFO. So it acts just like memory. We also took advantage of the FPGA's block RAM, which is why we don't pipeline the output signals of the block RAM and when they go to the WB stage. To implement multi-threading on our processor, we had to make modifications to our IF stage. Every thread needs to have their own program counter, and the instructions need to be interleaved within the instruction memory, as you can see in the image. We use a thread ID to select the correct program counter every single clock cycle. And also that thread ID is used to determine which program counter needs to be updated when a branch signal comes in.
To do multi-threading, we decided to go with a single instruction memory. And because of that, we created an interleaver for up to 4 programs because our processor is 4-way multi-threaded, and it interleaves them together and generates bytecode where every thread instruction is offset by its thread number. The interleaver is also where register renaming is done to split up our 32-bit register file between the 4 threads so no read-write conflicts take place. However, register 0, since it is ground to 0, is shared by all 4 threads. For our general processor, we decided to go with the RISC-V RV32i ISA from the RISC-V 2.2 specification. These are all the base instructions that we support on our processor, while we also support the macro op instructions that are specified in the RISC-V spec, such as load immediate, move, call, jump, and others. We also needed to create our own NF type, which stands for NetFPGA, for our packet FIFO that we use to communicate within the network. As you can see on the far right, we have the commands LSG, which stands for load signal, which is a polling command to see if the packet is loaded onto the packet FIFO. LTC, which is load tail counter, which loads the total length of the packet and allows us to iterate across it. RP, release packet, signaling the packet FIFO to release the packet back into the network. And CKR, check release, a 1-bit counter that increments when a new packet comes in.
So before we get into the demo, let's talk a little bit about the demo setup. As we can see on the right, our topology has a NetFPGA in the center, and it's connected to 4 nodes. To set up our program, we set our instruction memory and load unordered integers into our data memory. We'll then enable the CPU and kick off our program. The first 3 threads do a bubble sort, and the 4th thread will interact with network packets that pass through the NetFPGA. Finally, once the CPU is disabled, we'll do a data memory dump and check the results of our test. So now is part of the presentation where we do our demo. I'm SSH'd into 3 different boxes in several different terminal windows. I have N0, the control, which is our NF router, the server running the NF router, and then I have our N1 box as well. And so one of the threads is going to be interacting with traffic that's passing from node N0, which is our client, to our server running on N1. What we want to do is sniff traffic that's leaving N0 and then also sniff traffic that's entering N1 so we can look at the differences and make sure that our packet modifications are working. So to do that, we're going to be using TCP dump and just inspecting the packets. And we're also going to be looking at, on the server side, so on the server, to see what our inputs are when it connects and gets a packet. So let's get started. So the first thing we're going to do is flash our bit file using the NF download command. At that point, we can start the server and our TCP dumps on node N1 and then node N0. So our CPU loader takes in 2 things. We have the program, which looks like this, and this goes into the instruction memory and gets executed when the CPU is enabled. We also have our initial condition of our data memory that looks like this. So at this point, everything's ready to go. Let's run our CPU loader with our program and instruction memory. So the first thing we're going to do is parse our instructions, load them into instruction memory, and then set the initial condition of our data memory, as we can see there. Now our CPU is enabled, so we can quickly go run our client that sends 3 packets from the client to the server. And then we dump our data memory. So let's check out what happened. Okay, So as we can see here, we have 3 different locations in data memory for the initial condition. What happens is each of the threads go into our data memory, take those unordered integers, order them, and then after our CPU is disabled, we can go ahead and dump them. Now we can see they're ordered integers, and those are successful tests for bubble sort in 3 threads. Now additionally, we also have a thread that's modifying incoming packets, the payload part of the packets. And so what we can see here is my string 0, my string 1, my string 2 were sent through our network FIFO. We're modifying the packets to become my string 2, 3, and 4. And we can see that those were received on the server side correctly. So it's my string 2, 3, and 4 that was received on the server. And so at this point, we can say that this was a successful test because we have 3 threads running bubble sort and a single thread modifying network traffic.
In this presentation, we demonstrated how we designed a RISC-V compatible 5-stage multi-threaded processor. We also created a network FIFO that allows us to intercept incoming packets from the NetFPGA, then modify and release them accordingly. We then discussed our multi-threading architecture and our RISC-V ISA implementation, and we finally demonstrated our working processor on NetFPGA hardware by running the bubble sort algorithm on 3 threads while doing packet modification on the last thread. And that concludes our presentation, and thank you very much for watching.